key value pairs that kind of tell you more about that measurement that you just sent. Okay, so that's kind of a flexible, rigid structure, but you can send whatever key value tags you want, so that gives you some kind of flexibility for those kind of dimensions. So this is the kind of things you can send to it, but what can you ask it? So you can ask queries like, give me what was the average homepage load time, assuming that is the page load time, between 12 to 12:40 in segments of 5 minutes from users from China going into Hong Kong and from China into the Hong Kong data center. Okay, so the key is that when we send those tags, we don't just keep them separately. We don't say, oh, this is an event that is related to this server, and oh, here's an event that is related to page type is home. We keep the combination of the two together. Okay, so we can ask questions like when the origin was China and the destination is Hong Kong. So shouldn't surprise most of you, this kind of problem that we try to solve here. It's not fairly new. Why did we develop it ourselves from scratch? That's a good question, right? Work started a few years ago. At the time, graphite was like the only real solution to these kind of things, and it didn't really match not our model or our scalability. Today there are more options that are interesting. Most notoriously, very similar to this one is InfluxDB. But what we wanted was horizontal scalability, an event-like model aggregation, cross DC, and real-time response. So at the time it wasn't. Today you have things like Influx, but we still like our model because it gives us the flexibility to add small features exactly like we want them, and I will talk about some advantages of doing it yourself going forward. So what do we use it for? First of all, real-time application monitoring, that's like its most biggest usage, right? You send data to it and you can immediately want to see what's going on, are my apps happy? This is kind of part of our kind of philosophy, so if you're a developer, you should be able to have the tools to generate data out of your applications and also to immediately visualize this data yourself. So if you want to be able to own your own app and say like, okay, I know I did the right thing, I built it, I monitored it, we don't want you to depend on any other team that you need to talk to or something that you need to set up. It's all done from your perspective as a developer. So we use it mostly for that kind of real-time monitoring, also like technical KPIs, drill down, so you can kind of try to investigate what's going on if something is not working properly, and real-time alerts. It's also driving our experiment platform, so we have like this A/B test platform, and this is basically the engine underneath that, so it's kind of another win we got from building this system. So it's fairly big. Currently we have 1,500 different metrics that we send, up to 1 million combinations. What we talked about, the different that you have origin China, data center Hong Kong, page equals home, this is one combination, right? So we have around 1 million different combinations of tags per hour for a single metric in the worst case. And total we get around 300,000 input measurements per second, which is a trillion a month if somebody wants to see how to get a big number here. And the output is about 2 million queries a day to the API, which translates to 200 million Cassandra queries. I'll talk about Cassandra in a second, how we use it. So, what's the stack that we built this thing on top? The language we chose was Scala. We like Scala. First of all, it's a JVM language, so it's happy to work with other JVM products. So that's good for us in Agoda. We have quite a few JVM products now, like Kafka and Cassandra and Hadoop. So that's one thing. But it's not Java, you know. So you have the Actor model, which we like, high concurrency, multi-tenancy. The Spray web server was working quite fast for us. And the thing about Scala that personally I very much enjoy, and I think it works for these kind of applications the best when you have to crunch data across a funnel, is functional programming. And this is like what Scala brings to the table here most of all, which works very nicely in these kind of applications. So for the transport layer, we chose to use Kafka to actually push the measurements around. Kafka, we're already using Kafka quite heavily in other products, maybe we'll talk about them in next layers. relatively low delay. It's not like trying to get to the microsecond, but it's fairly fast. Good connectors with JVM. It's very high availability and redundancy. It's built for scale, and relatively easy to monitor. And the thing is that if you compare like Kafka, you have to separate things like Kafka and RabbitMQ and these kind of products. They are very different. So Kafka is like a queue where the consumer chooses what he wants to read versus there is no sense of a message that's being consumed or has not been consumed yet, unlike in Rabbit, for example. So that means that you can just send your messages and then any amount of consumers can come later and decide exactly what messages they want to read or they can read again. It's basically a database, right? So that would work in much better for this kind of application where I want to be able to scale and maybe add consumers, maybe have multiple services that read the same data over and over without committing it when I send a message. And lastly, Cassandra, why we chose Cassandra is it has no single point of failure. It scales horizontally. It has a fast write path using the block structure model. It has eventual consistency, which is good for this kind of project. But I don't care like if it actually happened this millisecond or happened a millisecond after. I don't care, right? Everything is eventual. I'm sending a measurement. It's eventually going to come. It has its own support for expiration. I will talk about also why that is not that great using the TTL setting. And actually, like we haven't invented any new concept here. If you go into Cassandra's own documentation, you will see they talk about the pattern of using it for time series kind of database. So that's good for us. We don't want to try to use something in a way it wasn't built to be used. And actually, future version of Cassandra that came after we did our work also even made it more like that. For example, if you talk about how Cassandra does compaction, now Cassandra has what's called time-tiered compaction, which is great for this kind of time series database. Okay, so let's talk a bit about Cassandra for anyone here who doesn't know it very well. Basically, it's what you call a wide column store, which is kind of one of the NoSQL kind of creatures that we have today. Similar to HBase, if anybody used, it's like the big two that has this model. Really like the whole thing about, you need to think about it, try to sell you like a two-dimensional table that you can add rows, but you can also add columns all the time. So that schema is not rigid and it can be added more and more and more. But if you want to think about it like SQL, it's not really like very different. Like I just write a record, and in the record I have two types of keys. I have the row key, okay, and I have the column key. And basically what I get is like some kind of a secondary index. So for which the same row key, if I try to do a range query over the columns, I'm going to get it very fast because it's going to be kept sorted. Okay? So if you want to think about it like a simple, like you think about a SQL table, it works, right? You have this row key, which is kind of, you have a composite key, which is the row key together with the column key, but you get this secondary index that if you just do a range on the column key, it's going to be fast. But otherwise, a record is just a record, right? So on the records that have the same row key, you get some guarantees that are going to be stored together on the same node, and eventually all the different columns will be sequentially on disk, so they will be able to do a range query quickly, and they are sorted. And just in the naming conventions of Cassandra, all the different records that have the same row key are called a row. But you know, we can think about it as completely different records. It doesn't matter. It's just about basically having this way to do a range query very quickly. So in White Falcon, we separate the data into two tables. We'll talk about them now. The index store and the data store. By the way, one thing to mention, like this kind of, they talk about how you can make the row bigger and bigger. One of the things you really want to avoid is to believe that statement. You cannot just increase the row forever. Okay, if you're going to get to hundreds of megabytes of rows, it's going to choke down your cluster of rows. I can promise you from experience, and it's not going to be working. I can go into the details why later, but just so you know, you want to keep it sane, like a few megabytes. Okay, so how do we actually keep the data here? What is the schema, and how do we actually keep the data? And that's why I was kind of going over and over about how much is just don't think about Cassandra or something that special, just basically a database that has some schema and a secondary index. So if you think about like the record we have basically two tables, if I'm simplifying a bit. One is called the index and one called the data. So the index, we have the name of the metric, time partition, time bucket, tags, and data store ID. Let me explain what it is and why do we have two places where we specify time. Okay? So the idea is that the row key is just these two columns. Okay? So these things that share the same values here, I know I'm going to be able to query very fast. So if two records have the same row key, they're going to be together. And the key here, that so I get the same metric and the same 6-hour partition, I'm going to be able to look at very quickly because they're going to be stored together. Now, well, you might say, why do you need the 6 hours, right? Just have the same metric all stored together. Okay, but that goes to my previous point. You have to limit how big those rows become. If you wouldn't have this thing and you just said, this is the row key, just metric, that means that all the data coming into one metric forever and ever for all history of humanity is going to be some ever-growing row. Okay? That will break your cluster very, very fast. So to limit that, you say, okay, I'm going to separate between rows by 6 hours, and then do the more granular separation inside the row. Okay, so then I have...
Last question?
Yes.
And how's the query is working? Like, why you pick to do it like 6 hours, not 2 hours or 3 hours? Like, you played a little bit with that, or?
Sorry?
Why you pick
Why
6
specifically
hours?
6 hours, right?
Yeah.
So exactly, the trick is to find the best balance between having a row that is not too big, but not too small. It's a Goldilocks problem, right? If I choose a really small number here, what's going to happen? What's going to happen is that I'm going to have very narrow rows, right? So just a few measurements, new row, few measurements, new row. When I will do a range query, right, my query executor will have to go many different rows, right? So that's not going to be a lot of consequent values there, okay? You understand? Because like every row is stored together.
It's like buckets.
Yeah, it's like basically like buckets of measurements. So on the other hand, as I said, if I'll take this value to be too big, my row just become bigger and bigger. It will be efficient to query, but because of how Cassandra internal workings work, it will find it very, very hard to keep those rows together on the same nodes, and then it will basically break on something called compaction. I can talk about, if you want to go into details of compaction, maybe that's for the end, it's a bit longer. So here I have this 10 minutes. It's not my final resolution, but I still have this 10-minute resolution here. And then I just have the tags. I don't have the values yet, yeah? Just have the tags. So for example, if I talked about the page load, and I'm going to use this kind of example a lot, the page load metric has this time partition of 6 hours is 12, but time bucket of 10 minutes can also be 12, right? It's 12:05, let's say. And then these are the tags. So we're talking about cluster is there, and data center is Hong Kong. And as I said, we keep the combination, right? That's what makes this problem actually not trivial. The fact that you want to keep the source combination as R. And then here you just have an ID. Okay, and that will link us to the other table I'm going to talk about in a second. But that's basically it. So that's one. That's basically one 10-minute. So this is per 10-minute bucket, but also per combination. Okay. So let's say this one is 6 hours, right? So I'm going to have 60 of those. Right? No, 36. No, 36. So I'm going to have 36 of those with the same time partition, right? Because how many 10 minutes you have in 6 hours? Right, 36, okay? We got through it. So we got 36 of those, but I can still have many different kind of those, right? And this is the unknown for me. I don't know how many different combinations I'm going to get, because I'm going to get a unique record per these two. So I don't know how many of these I'm going to get, and that's kind of my unknown here, right? If I knew exactly how many texts I'm going to get, then the Goldilocks problem of what's the best ratio here would be, would be easy. But I have an unknown of how many different tags I'm going to get. So that's basically going to be the one that's gonna affect the size of my row the most, the amount of different combinations I have. Okay, because this x36 is gonna stay x36 forever. The one of text, I just don't know what's gonna happen there. Okay? And what's the worst thing that can happen? Think about what if somebody sends a tag user ID 1, user ID 2, user ID 3, user ID 4. Okay, so if somebody by mistake, which for some reason happens a lot, sends a unique tag here as part of his measurement, basically my row will go, right? Because even in those 10 minutes, even in that one bucket of 10 minutes, the amount of unique tags that I'm going to get because of that unique user ID is just going to grow indefinitely, right? And then I get millions and millions of record inside one row key, and Cassandra goes down. Yeah. So that's like one of the biggest concerns when you have this kind of design. And just to make it the example full, so let's say another 10 minutes passed, right? So now my 10-minute bucket is going to be 12:10, but my 6-hour bucket is still going to be 12, right? Because that's how I shrunk it. And this is just an example. Let's say I got these different tag combination. Okay. So this is an example of 3 records, and this is the index. So as I said, the row size is mostly determined by the text combination cardinality. Cardinality meaning how many different tag combinations we got in that time span. Okay? All right. Next. So that was one table. We just have 2, so we're 50% there. This is the data store. Okay? So from this one, with this one we had these magic column that I haven't spoken about yet. This is the data store ID. With that ID, I can go here into the data store, right? And I can find it, and that is my row key here. So all I need to find the data store ID is just to have that ID from the index table. Now here, I'm going to get to my maximum resolution, which is currently on the 1 minute. And I'm going to say, every 1 minute, which is my sort column, I'm going to get just the counter, and currently, let's start with just the sum and the count, right? So if in that 1 minute, for the same tag combination, because this data store ID is for a specific tag combination, for that 1 minute, I'm going to keep what is the sum of all the values I got, and what is the count. Why do I keep sum and count independently? Because I can divide them one by the other and get the average. So I can easily calculate averages over those combinations, over those time ranges. Okay? So, for example, in the data store, I will have the data store ID can be the same, but for this different time step, I'll have it like this, with the sum and the count here. Okay? And because these are the sort column, that means that if I want to go from here to here in a single query, it has the same row key, then it will be easily to get for the database because it's already sorted in the storage level. So, just to be clear, let's take an example. Let's say my input JSON is something like this. The method is page load. This is the log time. The measurement is 10. These are the tags. Easily, because you have this log time, you can infer all the different partitioning that we just discussed. So eventually, there's only one record that needs to be created on the index and one record that needs to be created in the data store.
Can I ask about the behavior of Cassandra? How it's how it stores the data? Like you need to query all the time and just input in the specific data store, or you have some store procedures that it's doing for you?
So Cassandra in this case is, it's basically an insert. I'm not sure I'm following. You can do an insert. Where
like if you have some data that you want to store,
yeah.
And now you need to find for which data store you need to input this data.
Which
because
data
you have
store
like
ID?
Yeah, because you have 2 tables. You need to find the data store ID to input the data.
Yeah.
So you need to query the first table and then insert to the data store directly, or you have some store procedures doing it.
Yeah, let's put aside the store procedure, right? And just a fancy way to bulk like queries. Basically, Cassandra supports CQL, which is really SQL. Like all this part is very simple. Like this is a simple schema. You can think about it like literally like a simple schema of 4 columns, and here you can think about it like just a simple schema of 5 columns, and that's it. And think about like what you can do and cannot do in SQL. Now, the one thing in terms of Cassandra that you don't want to do is you don't want to do to read before write. You want to really, really avoid at all costs read before write. Why? Because Cassandra is optimized for fast writes. And the metric store, by definition, is optimized for fast writes. Okay, usually when you have a metric store, you're writing much, much more than you're going to query. Right? Because you're writing all the stupid bullshit that people are sending, but only some of it are actually needed. A small portion of it is actually needed. Okay? So basically, you don't want to interfere with the write process by doing reads. What Cassandra, how it does when you write, it basically just appends to a file and then does a compaction. So that's why its write process is very, very fast. Okay? So how do we do this without doing a read? This is actually what I'm trying to say in this example. You mentioned I have to write to the index table, right? And I have to write to the data table, right? The point is I don't need to find anything. I don't need to find anything because I have everything here. Okay, so I explain, or at least with some memory. So what we do is basically I can get all the time.
Sorry, because we are some attendee from live. Can you use microphone because they told that they cannot hear you?
Sure.
Yeah.
This one?
Yeah.
All right. I need echo. The mic configurable. Okay. Be like well, mitzvah show. That's good about karaoke. Yeah. I'll wait until.
Yeah.
Last question.
Very
No, not much.
No. It's on there. Okay, try now. No, still
The other side.
I can't see anything. It should be here. Have on the knobs. Yeah, it should be very low. Hello. Still? Yes, I think so. No, it's very no. Now? Now
Yeah,
I think it's now.
better. Yeah.
Now. Thank you.
Thank you. All right. So.
Pete is watching you from live.
Oh, really? I'll be more careful. So.
You asked for your session.
Okay, so we're talking about how do I get the data that I need to be able to write to those tables. So when I get my measurement in, the only thing I don't have at this point is the data store ID. Okay, so basically what we do, we know the data store index, right? Because we have everything we need to know and we have the timestamp. Basically, the only thing we don't have is the data store ID here. And the simple trick to do that is basically when I'm talking about how we actually write, the consumers that take these measurements of Kafka, they can just cache in memory the data store IDs for each index row that they create. Okay, the amount here is very, very small because these things runs, most of the time you get your measurement from just recent time, so the amount of IDs that you have open is not big. Okay, because like every 10 minutes you just change the ID for each tag combination. Okay, so that was.
How did you compute this data store?
You just hash.
This cache for this specific combination. Yeah. And it's unique for the metric and combination.
It's supposedly unique globally. So, I mean, I'm a little simplifying because like another thing we do is like we separate the tables by day because it's much faster, for example, to drop a table than to let things just get deleted, and that's why you'll get less collision problem because you also have that and stuff like that. It's not a problem to get it without collision. Okay, so the index, right? And when we read, we get like thing like this, which is the filter, and it says the data center I want is just Hong Kong, and it can be this, it can be multiple. So basically, you scan the index store first, and you get all the IDs that are matching this query in the time range. Okay, and now basically you have a list of data store IDs, and then you go, sorry, I didn't write this, so then you just go with those IDs to the data store and you get your data, right? And this, like, technically on the level of programming, this is done in a reactive way, so it's not like you're getting all the IDs and then you go to the data store, you run like, give me more IDs from the index store, give me more data, give me more IDs, give me more data, kind of thing in parallel. Okay, that's clear? All right, so we talk about the writes. So you have Kafka here, and then Kafka has multiple partitions. For anyone who hasn't worked with Kafka, Kafka has this notion of partitions, that how they achieve the distribution of the queue. So when you consume, basically each consumer, you're only guaranteed to have one partition used by one consumer thread at one point. Okay, so if you want to scale, you have more partitions. Okay, so by default, the data just goes randomly to all the partitions, right? And then you can have as many consumers as you have partitions to distribute your work. Now, what's the problem with that in this kind of thing? We basically aggregate the data locally here, and then we flash it to the Cassandra at each point in time. Now, the first problem you might think about, when you write to Cassandra, you can write, let's say I aggregated a few minutes here and I aggregated a few minutes there. Now I'm going to get a race condition, right? Because when I write the actual data, this one got 5 measurements, this one got 4 measurements, this one says the sum of the measurements in this time bucket is 40, and the other say it's 65. Okay, so they're going to just override each other. So what we did in this case, which was a mistake, we used counters, which is a Cassandra feature, that basically says instead of writing the actual value, you can send the difference of the value from the last value. And this is why kind of here I say it's counters, because it's like a special column type in Cassandra that means that you can send differential values to the store. Okay, but that solves for us this problem that how do we aggregate on different machines at the same time for the same tag combinations. I'll talk about how we changed it in a few minutes. Okay. So let's talk about the read process. Basically, what we have is user sitting here, and we have 4 data centers at the moment. So the user can hit any data center he chooses or she chooses, and then inside the data center, it goes to an HA proxy, which goes to the API servers, which just query the Cassandra, but it also proxy your query across to other data centers to say, do you have anything to add to this measurement? So the user can just query one data center and get aggregation of all the data it chooses. To do that, like this kind, we just have this kind of convention that the DC tag is about the data center. So we can be smart about it. So if you're just looking for values from Hong Kong, there's no reason to, no need to kind of proxy the query also to Singapore, right? Because I know people are just looking to query Hong Kong values right now. But if you're looking to do it, then yeah, we go everywhere and kind of break it down for you. Okay. Okay, so when we built this thing, it was pretty cool, and people liked it, except they didn't use it. Because it's a REST API, and as much as a REST API is nice and we like it, it's not as nice as just throwing things on the dashboard. Okay, so we noticed, okay, we can build, we have the metrics, we can aggregate them, but we cannot give people really interface to see their values. So that's what we looked at Grafana. I don't know how many of you know Grafana. It's a pretty wide-known project. Originally built to give a graphite alternative to Kibana. What Kibana gives Elasticsearch, they want to give to graphite. But the guy that built this actually at some point said, I'm just going to open it to every possible storage, metric time series kind of storage. It's very time series kind of oriented. Basically just give the interface, just give the UI to build dashboards on top of this different time series kind of solution. And this is a very, very successful project right now, also because of the inflation in the amount of different metric stores that we have today. like influx and Prometheus and Elasticsearch and all these other things. So the nice thing we could do is just take our solution. White Falcon is just basically build a plugin to make it work on Grafana. So the user can basically just go in and do something like this in our kind of language. Here, you can build and get all the visualization that you are used to get from if you use Graphite or whatever, but just in our kind of philosophy, if you want, that you can do like the group eyes, and you can say what you want to break down by, and you can do the tag filtering in event-like, and not the hierarchical kind of view that Graphite sees it through. And this was quite a big success. I think we have a few hundreds of dashboards that people created and used, so it's pretty nice. So what were the challenges of building these things? First of all, the problem that I kind of mentioned, extremely unique tags, right? So if people by mistake or just because they don't understand how they should use this kind of store, send a very, very unique tag ID. You know, as I'm keeping things in the raw level, I'm basically keeping as they send it, right? And when they say 300 measurements a second, that could come up to very much, and basically does not match the Cassandra model. So I can come to a situation to just aggregate a few seconds of data. I need to go over millions and millions of columns in the Cassandra, and it's not a real-time fast store anymore. It's Hadoop. So this is one of the big issues we had. The other issue is just people that send like loads and loads of measurements, so that also has a limit at some point. If every time you call the cache get method, you're going to tell White Falcon about it, okay, I'm not trying to compete with how fast you can get something from your own cache, right? That you assume that the metric store can handle every request you do to your own cache. It's not that fast, right? It's not going to be ever. So that's kind of like misalignment of how fast can it possibly go and how much data can it possibly consume. And the last thing is like complex queries. So let's say you take something very complicated, but you want it aggregated by the minute and give me the whole of the last year. So, you know, it's going to come up with a lot of points. You're not going to be able even to see the resolution, but you still ask the data store, and the data store is trying to be play fair with you and give you what you asked for. Okay, so a lot of these, some of these problems got solved by, at least this one got solved by the fact that we built the Grafana plugin, so it was no longer everybody trying to build their own visualization thingy, and we could kind of enforce all these kind of things in the UI itself. Like for example, if we see that we're going to make a query for, you know, 1 minute per year, we can block that before it goes out. Other things, we came with more complicated mechanisms that I might mention a bit. That's it. So the other thing is like hardware, you know, it's not as good as we think it is. And we have quite a share of these kind of problems, or just machines that are not configured the best way you can configure them. For example, HP has this feature called a smart drive. And if you get something from HP that starts with a smart something, usually you want to turn it off. Just by statistics, I can tell you. And this one, for example, gave us 10x just to turn this one off, for example. So you get a lot of these kind of things. We got all these kind of network issues. So we said we proxy across the network. Now you have to wait for this thing to come back. In the meantime, you're going to grow your heap while you're waiting. So these kind of problems. And data centers can completely disconnect from one another sometimes. So it's mostly about, you know, the real life challenges.
What do you mean by the heap grows? What do you mean?
So when I do the query that takes like give me Hong Kong and Singapore and aggregate together, right? So at the time that I'm getting it locally, now I'm waiting for Singapore to give it, and then I'm going to aggregate, right? But now I'm waiting a long time for Singapore to give it, so I have to hold my Hong Kong and, you know, values at that time, right? While I'm waiting for the data to come in. Now more queries come in and back up. It's not just the queries themselves, which are small. It's also the actual data for the queries that starts to build up, and that can grow quite fast. Okay, so protecting the system from those kind of issues. Basically monitor everything, look at the 99 percentile, and take your 20 worst queries at each point in time, try to see what people are doing that might be wrong. And you know, there's lots and lots of Cassandra metrics. I'm going to talk about that in a short while. So a few things we've done to improve ourselves. One of them is to block metrics with high cardinality. So what does that mean? So how do you defend yourself against that problem that people might send the session ID as a tag or the user ID as a tag, right? You want to say something like, well, I'm going to look at this, and when I see you sending too many unique values for the same tag or just unique combinations, I'm going to get upset and maybe I block you, or maybe I just drop a few of them or something like that, right? However, just counting how many unique values you got is also not a simple thing, right? But theoretically, if you want to do a proper count distinct, then you have to just keep a set or hash table of all the values you got and just see the size of that hash table, which would then become this thing will break before the Cassandra will break, right? Just to hold this kind of set. So we use the algorithm. I don't know how many of you heard about it. It's pretty cool. It's called hyperloglog. We have the hyperloglog++. That Google kind of did some improvements to. And just a very cool algorithm. I'm not going to go into the details how it works, but it's very cool to give you an approximate count distinct. And the lesson here for us, like a lot of times when you try to do something like this, like to do it accurately is really, really hard. But to get like a good approximate, and for this kind of thing, like approximate of 5% is excellent, because I'm just trying to get, you know, in general, are you sending too many, yes or no? So to get kind of estimation, you can do with a finite amount of memory and a finite amount of computation time. So that's really cool. And then when we got that, we can start aborting queries that are going to hit too many different combinations, and that kind of solved all the problems of not knowing how complex the query is before you actually start it. It's basically our query planner. And as I said, the Grafana itself is helping us to control how people are using it and to make sure they don't abuse it. And the one mechanism we have is what we call projections. So let's say we know we have this, let's say we have two tags, cluster and DC, right? So, but we see that actually people always query by just using this tag, right? They don't usually query using this tag. So what happens in every query is that the database is going and taking this item and doing the average again and again every time. So what we do is basically like a materialized view. We also have another table that just has the combination of these two rows, which keeping just those specific tags. So we specify some tags that you just keep them aggregated. Now when a query comes in, we can choose if we go to the projection table or to the row table. So the user always gets a correct response and with the amount of resolution that he wanted to get, but we can give him a much better answer if he asks for a different amount of text, which before it has no meaning on performance because you have to go over everything anyway.
How did you choose the high open combination of tags?
Right, so currently that part is done manually. So we just have like an API to do that. So we ourselves define like the team that manages this. And that's why we have like good monitoring, so we can actually see like the bad queries coming in at all time. And then we just add a projection. But yeah, we're talking about to do something like more clever that will add them automatically, but obviously you can see how that can go wrong very easy. So we still do it on the manual. Okay, so that's basically what I want to say about the general topic. I want to dive into one problem that we solved rather recently, maybe 6 months ago, which is also interesting, and that is how to support percentiles. Okay, so why do we want to support percentiles? Because like basically we in Agoda we define most of our KPIs by percentiles. So we talked about the page load time, but nobody cares about the average page load time. It doesn't mean anything. We care about maybe the median page load time, maybe the 99th percentile page load time. Okay, why is that? Because if I tell you the 99th percentile page load time is 100 milliseconds, okay? So you know for sure that 99% of your users are getting the 100 milliseconds. Now that 1% that's left out of it, they might wait for 5 hours, you don't know, right? But at least you know what you gave to a specific percentage of your users. When you get the average, you don't really know like how many users get a good experience and how many get a bad one. You get just a number that you can kind of look at. And this one is more stable. So another thing is that you do 99. Let's say I do something, I have a mistake, I have a bug, and it only hurts the bottom 2% of the users, right? I might not see it in the average, because it might be, okay, just bottom 2% of my users. But if I look on the 99, I'm going to see just that, right? It's going to come up as like the only thing that I see, because I'm only looking on that worst 1%, on the border of the worst 1%. So if something is hitting the bottom 2%, I'm going to see just that. It's going to be obvious to me that something is wrong. And to give this example, this is a real example of something that went wrong at some system. And then you can look what happened to the average, which is the yellow line, and what happened to the 99 percentile. Okay? So when you're looking on this dashboard and trying to see where the problem started and where did it end, look how much of a clearer story the 99 percentiles are telling. You can see very, very easily that the problem started here, and you can see that it actually been all the way until here, that it actually went away. And the mean is also telling a similar story, but it's much more like, I don't know, I think it started around here, here it was really bad, and then it started to become good, so here you get a much more clear story about what's going on. And that's why we love percentile, but at the same time, why do we hate them? We hate them because they don't aggregate. Okay? So what does that mean? When we talked about the sounds and the counters, I went from 1210 to 1210 to 1220. If I had a sound 100 to count 10, sound 80 count 50 here, I can say that exactly between 12 to 1220 I have a sound 180 and a count of 60. Right? That's not complicated arithmetics. And then I can easily get the average. Right? So I can say accurately that the average in this amount of time was 3, right? Where here it was like 1.6 and here it was 10. Okay? So I can get the accurate averages aggregated. However, the same kind of notion doesn't work with percentiles. If I know that the 99 percentile was 75 in this time period and the 99 percentile was 85 in this time period, then that's nice for me, but I have no idea how to aggregate them together. So what was the value of the 99 percentile between 12 to 1220 from knowing these two? Any ideas? Good, because it's impossible to know from this amount of information, right? So that's kind of annoying. Now, some other solutions like graphite tell you that you can look on the 99 percentile and then you can open and zoom out. But what they do is kind of lying to you. Okay? What they do is the average. They take the 99 percentile at the resolution they have, and then they average those values. Okay? But that could be really, really wrong. Because, for example, if you have, let's say when you aggregate across time, it doesn't sound that bad. But think about it, what happens if you have 100 servers, right? And one of them is going wrong. Then it will just average between the servers each 99 percentile. So you don't really get the 99 percentile of your experience. It should be only that server that's going to be that. So it can be very far away from what you want. So how do you actually support percentiles? And this goes to the same point I was making. Some things are really, really hard to do accurately, but actually very, very possible if you're willing to take some approximate of what you're really trying to calculate. And this is where the cool algorithm, and it's fairly new, it's like just 3 years ago, which is nice because you don't get a lot to actually implement an algorithm so new, which is called T-digests. So we couldn't have done this like 5 years ago because it wouldn't exist, the idea. And I will just kind of go into the details of how this algorithm works because I think it's fun, and continue from there. So what's so great about those T-digests? Right? So basically it's an algorithm to calculate percentiles, but they give you a configurable amount of accuracy. So you can play with the trade-off of how many storage you want versus how much accuracy. Just let's make a short stop and ask, how do you calculate percentiles? Right? So you know, right? You take like the naive way, take all your values, sort them in a row, and if you want the 99 percentiles and you have 1,000 values, go to the one position, then 9,900, and that's your 99%. Okay, that's the naive way. So that means storage-wise, the more values you have, the more storage you need to calculate the percentiles. And it also means that if you want to aggregate two different numbers, you have to keep the sorted list, do a resort, and then get the percentile again. If you want to merge two kind of buckets of time. Okay? That's going to take too much time. So how is this thing helping us? So the t-digits have some very cool properties. First of all, and that's like the really new thing about it versus its predecessor, is that the accuracy is guaranteed relatively to the requested percentile. What does that mean? So let's say you want the median, right? What percentile is the median? The 50, right? So you want the 50 percentile, and I'm going to give you 50.1. Are you very upset? Yeah, it's okay, right? Like I just said 50 because I like things that, because we have 10 fingers, right? That's I said 50. 50.1 is also okay for me, right? And if I give you by mistake 49.9, you're not going to be angry at me, right? So if I did plus minus 0.1 on the percentile, you're not going to be terribly angry. But if I ask for the 99.9 percentile, and then by mistake I give you the 100, that's a big deal, okay? Or if I give you the 99.8, that's a big deal. So having a mistake of 0.1% of the percentile can be a big deal if it's a percentile on the edge, and can be not a big deal if it's a percentile in the middle. Okay, so that's the kind of cool thing about this algorithm. When you define your accuracy, you define it in a way that is relative to that. We'll see that in a second, but that means that basically I will give you a much better, if you ask for a even if you ask for a 50, I give you 50.1. If you ask for a 99.9, I will worst case give you 99.901, which you should be okay with. So, so that's the really cool thing about it. The other thing is that it allows aggregation of itself. So let's say I calculate the t-digest of this time period and the t-digest of another time period, and I want to ask myself what is the t-digest of the total period. They can merge, they can consume each other and create one t-digest that talks about without going back to the raw data, which is a very important feature. The data structure is bounded in size, which is important because otherwise I will blow up at some point. And it's an online algorithm. What does that mean? So in some algorithms to do this kind of things, you have to know how much data you have when you start the algorithm. So let's say I'm going to calculate percentile for 1 billion points. You prepare something, and then you run them. Okay, here are the percentiles. But here in my case, I don't know how many points I'm going to have. And actually, when I aggregate, I actually increase that size all the time. So there's no way I can prepare in advance to know how many points I want to calculate percentiles for. And the nice thing, which is a kind of small bonus, is that you always know the maximum and the minimum accurately. Okay.
So the data structure size is bounded by what? By the accuracy?
When you set the accuracy, you will basically know what is the bounding size of your.
Okay, so it depends on the accuracy.
Yes, you have the trade-off, you can play with it. The more accuracy you want, you'll have more storage and you will have more CPU time, which is because you have a bigger structure to go through. I will just go now into the details. Yeah, that's the most. That's the hard part, but it's not that hard. It's actually cool because up until now, what I told you sounds like magic. And now you see it's actually quite a simple and nice algorithm. And if anybody has some experience with algorithm, you can think about it a bit like a kind of a online k-means algorithm. And if you don't think it like this. Let's go over it, right? So I'm going to just run the algorithm on the board, and then we can kind of talk about it. So what do we have here? Let's say this is the time dimension, went like this. Okay, these are the measurements I'm getting on my inputs, and this is the structure that I'm keeping. Okay, so first thing first, I get one measurement. The measurement is 2. Okay, that's the number I got. What do? I keep this kind of list of centroids. Centroids are basically a tuple of a number and a count. Okay? So what I'm going to say when I get these 2 is not very clever. I'm going to say I got a 2 and I have one number. Okay, so this is the count, 1. This is one centroid, okay? Now I got another number coming in, it's a 4, okay? This is not bingo, nobody wins, but now I'm gonna do something not very exciting and just create another centroid. This time I'm gonna say the value is 4, and I have one number. So far, I didn't really decrease the amount of data that I need to keep, okay? Next thing I'm gonna get is an 8. Still not very exciting. I'm just gonna put this 8 here and say I have one of those, okay? But now the magic happens, I'm gonna get a 6, okay? Now this 6, instead of creating a new centroid, what I'm gonna do is I'm gonna merge it with this centroid that is currently in 401, and I'm gonna say the average of these two is 5, and I have 2 here, okay? So now this one did not take any more memory for me to do.
That's why you have to know the amount of data.
Sorry?
That's why you have to know the amount of data.
No, you don't,
How
in this,
much centroids.
I will go into this. But in this algorithm, you don't need. In this algorithm, you don't need. I will explain how it works. That's the magic. So now you get another one. This is a 12. I'm going to create a new centroid. I'm not going to merge it. Just going to put it here in the end. Okay? And then I get another one, 16. Not going to merge it. Just put it in the end. Okay? And now I'm going to take this structure and I'm going to feed it to itself. I'm going to run it over itself. And this time, the magic will happen, and this will stay the same, this will stay the same, the 16 will stay the same, but these two will merge. And instead of an 8-1, 12-1, I'm going to get a 10-2. So I reduce the size. Okay? So how do I know, and why do I know how to merge, when to merge samples together? Okay, that's the big question. Basically, the structure is very simple. I keep like averages and how many points rank into the average. The magic is to know what points to merge together and when. Okay? Now, this is where this formula comes in. 4q1 minus q and delta. Okay? Now you understand, right? So let me explain. So the delta is is just my freedom of choice. That's my trade-off. The bigger it is, I need more storage, and I'm going to need more CPU to process it. Sorry, the smaller it is. The higher delta is, I need less storage. And let's talk about the other ones. So n is the amount of samples. But I just said you don't need to know the amount of samples, right? So here's the cool thing about n. It's not the amount of total samples, it's the amount of samples you got so far. So n actually grows, each sample you get, you grow it by 1. And q is the estimated percentile of that sample you got when you got it. So here's the cool thing. The algorithm is using itself. The algorithm is calculating percentiles in order to calculate percentiles. Okay? So when I get a sample, I use the algorithm on what I currently have. So let's say I got this 4, right? And all I had is this 2 and 1. So I went to the algorithm and said, hey, you have a 2.1. What's going to be the percentile of a 4? Okay? The percentile is going to be 1, because it's going to be the maximum. So Q is going to be 1. Q is like where I am, 0 to 1 kind of percentile, right? So Q is going to be 1. So this thing is going to zero out. Yes? So this thing zeroes out. That means that the centroid that is going to hold this has no room. Okay? Has 0 room. Now, let's go to this place. I get the 6, right? I got the 6, so I'm moving over my centroids, and when I get the 6, these are my centroids, right? And I check this centroid. What is the calculation of this for this centroid? N is equaling 4 right now, because this is my 4th sample. And Q is different between the centroid. This centroid is going to be 0, because it's the minimum. Its percentile is 0. And this one, percentile is 1, right? Because it's the maximum. But this one, percentile is like 20, I don't know, it's like 50, right? It's the 50th percentile. So now this thing doesn't zero out. So 4 times half, you get 1 times n times delta. So it becomes just n times delta, and n is equal 4. Okay? So in this case, because n equals 4, if your delta is bigger than half, then the result of this is going to be bigger than 2. And if this is bigger than 2, then this guy actually has room for another friend to come in to live with him in his centroid. Okay? So then this 6 comes in, he can join this one. And this is how we make this decision. And what the mathematics comes in is to prove that I will never regret. Because once I put things together, I obviously cannot decompose them back. I cannot say, oh, I got these more samples, now I know that actually you cannot, I shouldn't have added the 6 in, right? But that's where you can actually prove that that never happens. Because because n grows all the time, you get more and more samples, you just get more and more room everywhere. So even if your thing that you thought is going to be, maybe after this one, it took me a lot of time to get convinced that this is working. So if this is sounding like not good for you, that's good. If you think that, yeah, now it's the 50 percentile, but maybe I get 1 million samples now that are all here, and this will be a very high percentile. And then this equation will say, hey, what you're doing, you don't have room for that thing you put in there, right? You don't have the room. But when I get 1 million more samples, also n will grow, because now I have 1 million samples in. So you can prove that this thing only grows per centroid. So that means every centroid, no matter if you got the percentile wrong at first and it moves back or forth, it can only grow. Okay? And that's a really cool thing and surprising about this. Now, what can happen is that you have actually more room than you think. Maybe you've been pessimistic. And that's what's happening here. And the worst case, if you think about how it works, the worst case if you get your numbers sorted. If you got your numbers sorted by mistake, because that's how the user sent them, it's always going to be the highest percentile, or the lowest, depends how it's sorted. So if I get consecutive numbers, for example, 1, 2, 3, 4, 5, 6, 7, it's always going to be, oh, I'm just getting the maximum, oh, I'm just getting the maximum, just getting the maximum. I'm going to build, like I had here, more and more centroids. And then, the cool thing is that every once in a while, you stop, you randomize the centroids, and you feed them back to themselves. And that's what happens here. You can get to this position where you actually reduce the size. Now, to ask the question, how do you actually query this structure? Okay, that's great. You did this nice exercise. How do you actually query this thing? So it's actually easy. Now, if I want to know, after I have this kind of structure, I didn't know, by the way, up until now, I didn't say what percentiles I'm going to calculate. Okay, I don't have to commit on what percentiles I want to begin with. Now that I have the structure, I can say, oh, I want the 70 percentile. So I can say, okay, how many samples I have in total? I have 6, right? Because I have 1 plus 2 plus 2 plus 1, right? That's 6 as far as I know. So the 70 percentile is 4.2. So I'm going to count until I get to the 4.2 area. I'm going to get this bucket. And this bucket is a 10. So that 70 percentile is a 10. Right? So way to go for the guy who wrote this algorithm. Very cool.
So how does it make the storage finite? Or if it grows beyond what you want, you just compress it?
Well, that's a bit harder to prove, that it actually converges.
Okay.
For a specific data, it converges. The size
Because
doesn't
it
grow at
keeps
some point.
growing after.
Yeah, I'll tell you I'll tell you the intuition across why it needs to converge, right? After you got let's say your class you want 0.1. After you got 1 million samples, it doesn't matter anymore how many more samples you have. Right? One of the common things to do for placenta is just to take a sample. So that kind of tells you what's going to happen at some point. You're not going to learn anything new about the statistics. You're just going to have, oh, this one can grow here, this one can grow here. Because this thing always grows. So the centroid size always grows. Okay, so you can store more and more. The only reason you have to add more room is because you find out a part of the statistics that you didn't know about. But after a certain amount, assuming your thing that you're tracking has the same statistics over time, you're not going to need any more storage for that. Okay? The only reason basically compressed because it's when you get things in a non-random order. And then if you already got 1 million samples and everything is compressed, the only thing when you have to do a lot of work is if you think about you got now that the statistics completely changing. And then you have to have a lot more centroids to kind of take over that. But after compression, it will also go down again.
Just one question, when do we compress? Is that just
Every
heuristic,
like
or
1,000 samples or something like that.
when do you want to?
Well,
Or
it
is
depends.
that-
It's a CPU question, right? Because the problem it's a storage CPU trade-off. Because like if you don't compress, you're going to use more storage more time. When you compress, you're going to use a lot of CPU to do it.
Okay,
that's
so
it.
it's my choice to do.
Yeah,
It's
exactly.
not like
There's no, you can do it.
Fine.
I think we do like every 1,000 samples, something like that. And you can understand that because the compression is basically feeding the algorithm, the merging structure to itself, the same way you can merge two of these. You can just take one of these and another one and just feed them to each other, and you just get like the aggregated T-digest.
So you started this table once per minute?
No, I'm storing this thing once per tag combination per minute counts and counters because I just merged them together in query time. I do this process of compression, as I said, you can also do it between two digests that are different. Because you can feed the T-digest to itself, like go over it again, you can take two of them and just pull them together and get a new T-digest that represents the sum of them, right? So that's what we actually do in query time. We keep those little thingies on the single tag combination on a single minute. And when you query over a range of tags, we just get a lot of them, right? And then we feed them together and get just one back. Okay, like I would do for a simple sum. If I enter some number, that's obvious how I do it, right? But the combination operator exists here, which has the same properties as a sum. Like, being associative and commutative and everything. So that's about that. So the only problem we have now, if you remember, I mentioned how I write to Cassandra. I use those counter thingies in Cassandra, so I don't have to worry about different consumers writing over each other, right? Now here, this problem is coming back because I'm not going to be able to use a Cassandra counter for this, right? This is not a counter. This is a structure of a list of centroids, which is not supported natively by Cassandra, believe it or not. So I have to actually make sure that I don't have this kind of collision, right? So how do we do that? Basically, we kind of reuse Kafka. By the way, it's a nice function that you can do a lot with Kafka, consume and then write back, consume, write back kind of thing. And basically, we take those things, we aggregate them locally, but then instead of writing to Cassandra, we write back into Kafka. When we write back into Kafka, you can make sure that you put the same tag combination in the same partition in Kafka. Okay? So you can make sure that when you write it back, those local aggregates will come to the same partition if they are about the same tag combination. And then there's this consumer here, that aggregate consumer that gets them is guaranteed to have just one partition for the same tag combination. You can have still many partitions. You don't have to have just one consumer. You can have many, but per partition, you're not going to have a 10 combination that is on more than one partition. Okay? And like we're trying to move everything basically to this structure because like the Cassandra counters are not very well performed. Okay, so what did we learn? A lot. A few notes about what we learned. So first of all, Scala is an easy language to compile, like hello world kind of thing. If you want to do Scala well, like I advise you, get into it, learn the ideas behind the language. Don't just see if you can like run a hello program. The functional programming, if you haven't done it before, is very different, and it takes some time to get used to and really get the most out of it. So that's one thing that's easy mistake to do. Akka. I don't like Akka. Like it's very good PR. The website is like, oh, we've been stupid all these years programming. We should have used the actor model for everything. It's perfect. There's zero things wrong with it. Okay, I disagree with that wholeheartedly. There's a lot of things wrong with it. one of the things I can mention, if any of you has any experience with Akka, anyone here have experience with Akka? I assume some people from Agoda for sure. Okay, so what is the definition of the actor? What is the signature of the receive function? The receive function signature is you get any, and your output is unit, which is the worst signature of a method ever in the history of the universe. Because basically it means that your compiler is not checking what's going in at all. You can send whatever message to whatever. You just took the compiler and threw it out. You can use Python if you want, and at least you get nice patching capabilities. And you cannot compose it because the output is unit. So if you want to say, hey actor, after you do this, please tell this other actor, you have to give him the actor and tell him what to tell him. You cannot just link things together. So if you ask me, futures are the future. They are way better than Akka, not as good homepage on the internet, but much, much better abstraction. But that's like my own thing that I'm trying to push people away from Akka. Kafka is all fun and games, and it is like a very, very good product, I have to say. From all these distributed products, Kafka is the one that like really gave us good, relatively like low amount of problems, relatively, until the disk is full, which is okay, right? It's fine. You cannot ask too much of the system to do when the disk is full, but just like put all your alerts on this thing because it's gonna make your life living hell if it's not. And you have to understand this kind of Kafka semantics about the at least once versus at most once. Don't go into it, oh, I have a consumer, I'm done. You have to understand what are the offsets. You're gonna commit your offsets after you're processed or before you're processed, okay? What are you more worried about? You're worried about losing some values, or you're more worried about duplicating some messages, okay? And you have to make those decisions and make sure your consumer is actually doing what you think it's doing. And Zookeeper, not a great product. So Cassandra, it's been a long kind of you know, it's like marriage. It's all fun and games, and you know, when you have just get married and everything is working, but then you have a few children and you get into this, right? So a few things we learned. Kafka is a complicated product on many, many issues. We had the case I mentioned with the hardware. The JVM, you know, it's not happy to manage so much data to be really realistic. So like you get things like the GC you really have to look into. Compactions are a big issue in Cassandra. Compactions, like this whole thing about Cassandra being super fast is because it just writes the data directly without trying to put it in the right place for fast query. And then that process of saying, okay, let's reorganize the data so we can actually get to it quickly is done after the fact, it's done afterwards, okay? And this is the LSM structure, and it's very successful in their databases, the level DB and whatnot. But this thing, you have to know that you're going to have this compaction. Whenever things are going in and you're very happy about it, you have to watch your compactions. If they go high and don't go low, the cluster is going to go down. Watch your row sizes. That's also kind of talks of, when you compact, you basically have to take the whole row together. And that's going to be a problem if your rows grow indefinitely, as I mentioned before, because you have some unique tab. So you have to watch your row sizes and monitor that. The hints table, same as above, it's nice, this cool thing that Cassandra, if you lose a node, then the other nodes are going to be nice to it and just, you know, take his homework home, basically keep all the things that they think he didn't write yet. Okay, and just keep it called the hint table. Now this table, at least in Cassandra 2, is horribly implemented, and we lost clusters quite a few times because of the hints table being too big. Okay, so in most cases we just disable this mechanism. Counters, don't use them. It's very easy. Sorry? We tried 5 minutes. We tried 5 minutes in the group. The counters, don't use them. Basically, I mean, that structure that you aggregate for Kafka works much better. The internals of how it works, theoretically it works better in 2. We didn't try, so we're still using them to some extent, but we know we're paying a lot of cost for using them, like 5x in the query time. Deletes, you know, you have the TTL, it's so cool, I can just, my data expires, don't use them. Try to drop your whole tables if you don't need them. Like if you work by a time series like we do, just do the same idea. work with like daily or weekly tables, where you can flush down the whole table, and then you don't have to worry about how deletes actually work in a database like this. Basically, a delete in Cassandra is like another write that needs to be compacted. And then the run repair, so because you can't really trust that you're gonna, if some node came back, you can't really trust that it really like synchronized with the others. Definitely when you don't have a hints table, then you want to run repairs periodically, which basically like this process that makes sure that everybody agrees on what needs to be the data in the cluster. And again, disk size can grow, and the problem is that when you're gonna have a high load, not only you're gonna write a lot so the disk will grow fast, you're gonna have more compaction, which means the disk grows even faster, because in compaction time, it's basically doubling the size of the disk. Depends on your compaction strategy, but it can go up to that. That's it with this note. Any questions?
Do you remember any interesting case with customers which you found with this system and new solutions? Maybe some crazy sort of stories?
Crazy story. I know, one of the things that, I don't know if I can qualify for a crazy story, then I feel like it's a lot of stress to find something. No, I feel like I mentioned that the time that they started sending the user ID was like a very crazy story kind of thing, because like, you know, you take a cluster that is basically healthy and then it just went down like a rock. Now, to get rid of something like this is like a lot of work, right? Because like, you can't really isolate those evil rows in an easy way. Now the stuck, it's like having someone go to the hospital with things stuck down his throat, right? Because now it's going to be compacted. How do you remove it from going to be compacted kind of thing? So those are the kind of issues that we had. I don't know if I can give you like more crazy stuff. This is not like, not crazy.
So, I'm just curious, like, if you are going to like decide this today, will you change to some other storage?
Yeah, that's an excellent question.
That like maybe more suitable to what we are doing. I'm
Yes.
just curious.
Yes. So the only thing is that, I've been thinking about that a lot. The only thing is that I would think is like the problem with, or like the thing about storages like Cassandra and all these level DB kind of databases that came up like, I don't know, 10 years ago, is that they were really trying to optimize for the spinning disks. Because at the time, to get a big SSD was basically impossible or very expensive. So the whole point was, how can I make the least amount of seek times? Okay, so how can I make myself that I don't jump around as much as I need? The least amount of jumping, and that's why you write ahead, and then you go and you compact in one go, right? I'm not sure that like with the SSD world that we live in, this is not as big as a need as it used to be. And some new databases like Aerospike and ForestDB, which is the new storage for Couchbase, they're trying to optimize not for this kind of pattern, but more for SSD assumption. And Aerospike is even going another step and saying, well, I'm assuming most of your data is going to be in memory. Okay? And the patterns, when you have, like, the patterns that how you want to write data when you're assuming most of it are going to a memory or SSD store, is going to be different kind of optimization. So that would be something I would do.
Like, so with complete ignorance of how these things work, would you just like show up with Elasticsearch? That would help you. That would probably help with your the query part of it. But would you do that?
Elasticsearch would not be a very good store for this, because like what I have here, I have quite a rigid structure, and Elasticsearch, you know, it's a document store, so it's allowing too much structure, and therefore not have the right level of optimization that I can have because I know my structure. Right? So Elasticsearch will probably not be able to get to the same level of performance that I can get with a more rigid schema. Any more questions? All right.
About color website, if you have the HTML color,
you want to update the data which you have the wrong record to this one, is that how hard?
So again?
If you have the bad record into your weapon, right? How hard is gonna affect everything, data, like the liability. If you want to, this is like the counter database, right? It's not relation. When you add the data, it's not gonna, cannot revert, right?
Again, when I add the data, it's not this data.
Once if the data.
Yeah, when the data go in, it cannot be updated, right?
Cannot be updated?
Yeah, is that, can this, the data be updated after it's gone?
Okay. That's a good question. So, yes and no. So it's not like you can add more information about things that happened an hour ago and 2 hours ago. It's not a problem because it's all counters, right? So it's all differential. So I can say, I can add now for events that happened an hour ago. This is, by the way, another thing that we liked about this versus Graphite, because Graphite doesn't have this ability. And sometimes we have a problem with the Kafka and we want to rerun this amount of time and so forth, right? So basically, we haven't built this tool, but what you can do is you can kind of go back in your time and start cleanly like rewriting parts of the history. So you can do it. It's not a trivial thing. It depends on how much the granularity of your table is, right? So if you're working in the 1 minute resolution, right, then you don't have a problem to delete those minutes and rewrite them if you have the raw data, right? If you're working in hour resolution, then you have to go at least 1 hour back. See, so the problem is we have some cases where I think you know one of them is that we have a 1 year resolution, right? That's a specific use case in the experiment platform, and then basically you cannot because everything is aggregated in one number per year. So you have to go consume a year back of data to be able to replay it. But
Can you calculate it from the beginning?
so if you have that 1 year of data, but we don't. We don't keep the measurements, the raw measurements, so far. So by the way, like in that case, I just suggest not to use ever this kind of resolution. They never work in something that is bigger than what you can go back. Like usually it's okay. You don't aggregate 1,000 years. You know. Anything else?
That how long data keep on your system?
So it depends where. The Kafka itself keeps the. If you have a problem, you can just consume. Like if you consume a data or something, you can just go back and up to 3 days you can handle it. In the Cassandra, we keep it in different resolutions in different time. So we have the 1 minute resolution, 10 minute resolution, 1 hour resolution, 1 day resolution. The 1 day is kept forever. The 1 hour is like 1 year back, and the 10 minutes and minutes is like I think a month.
Okay, I think we are at time. So, let's come back in 10 minutes for one last presentation.